Okay, so now I have an insulating sphere with non-uniform charge density. So it's insulating sphere where the charge density rho increases linearly as a function of r. So the picture looks something like this. The person places some charge here, and then they start to push out, push out, push out, but they don't completely push out. So what ends up happening is at the center, there's no charge. But then as you go out, you begin to encounter more charge, but it's still not that much. But then as you go towards the edges, more charge is beginning to appear, you see? So most of the charge is right here. You see, it's linearly increasing. Most of the charge is distributed towards the edge of the sphere. So what is the electric field? Now, outside of the sphere is not going to change. The answer is still going to be kq over r squared. Because remember, we saw that it doesn't depend on the distribution. Inside, we're going to do the same kind of process. And we're going to say, we're going to take a certain radius r. And we're going to apply Gauss's law to the inside. So again, we have EA is Q enclosed over E0. Okay. The trick is always to find what's the relationship between Q enclosed and the total charge of the sphere. That's really where the only difficulty of the problem is. Okay. Now, in this case, since the charge distribution is not uniform, you can't say the Q enclosed here divided by the total charge. You can no longer say the Q enclosed divided by the total charge is equal to the volume enclosed over the total volume. So you can't say that anymore because it's not uniform density. So you're going to have to do an integral. You're going to have to say, okay, the Q enclosed dq is equal to rho dV. Rho is defined as the volume charge density. It's the amount of volume in a certain small, it's the amount of charge in a certain volume. And if I want to find the total charge, I integrate the rho dV, where my dV is small spherical it's a spherical shell. Okay? So dV is the volume of a spherical shell. And the rho tells me how much charge is included in that shell. So dV, what's the volume of a spherical shell? It's 4 pi r squared dr, right? The area of the surface area of the sphere times the thickness of the shell. So 4 pi r squared dr is the volume of a spherical shell. And then rho is equal to kappa r, linearly proportional. So I get Q enclosed is equal to kappa r 4 pi r squared dr from 0 to little r. And then the Q enclosed is going to be the 4 pi kappa comes out. Then you integrate r cubed dr from 0 to r. And you get 4 pi kappa r to the 4th over 4, which is pi kappa r to the 4th. So what I got is some kind of formula that tells me that the Q enclosed within a certain distance little r is equal to pi kappa little r to the fourth. But I'm going to have to now do another integral to find the total charge of the sphere, because my ultimate aim is to relate the Q enclosed to the total charge. You see, to find their relationship. So I do a similar integral now for the total charge. The only difference now is, you know what? I don't have to redo the whole integral. The total charge is going to equal pi kappa big R to the fourth. Right? Because if the Q enclosed is pi kappa little r to the fourth, so once you get to the total charge of the sphere, it's pi kappa to the big R to the fourth. Therefore, here's what I'm going to say now. Pi kappa is equal to Q total over R to the fourth. So now I can substitute that there, and I reach my final goal. Q enclosed is equal to Q total over R to the fourth times little r to the fourth. So I found the relationship between Q enclosed and the total charge. So let's see if this makes sense. If R equals half of R, how much charge is included within half the sphere? 1/16 of the total charge. With the uniform charge distribution, what was it? 1/8. This one is less. Does it make sense? Yeah, because the charge density is increasing, more charges on the outside, so it makes sense half the sphere only has 1/16 of the charge. You see? So now you know how to do this general process. Like on the test, I could say rho sub r is kappa r to the square. That means it increases more rapidly. Or kappa r to the cube, kappa r to the fourth. Now once you get that, then you put that over here into the Gauss's law. So really the only hard part of Gauss's law is, this part is easy, it's finding the Q enclosed, is the process. Then you go and you say E times 4 pi r squared is equal to Q tot over r to the fourth times little r to the fourth and over E0, and then you're going to have the answer K Q over r to the fourth, and then this cancels this r squared. KQ r squared over r to the fourth. And then you can do your two checks. If little r equals 0, you should get 0. And then what was our other check? If little r is big R, you should get what? KQ over r squared. You see? It worked out. Because at the surface, it should look like a point charge. And again, when you can graph it, the electric field as a function of r, and it's going to look this time as a square function, and it goes to the same value, KQ over r squared, big R squared. There, this is big R. So it's a function of r squared. So it goes as r squared, then it drops as 1 over r squared. So the electric field increases less rapidly at the beginning. You see? Then the other one increased linearly. It increases less rapidly in the beginning, but then it increases more because more charge begins to come in as you go farther out. It makes sense. It's really beautiful. Okay? So if you're really understanding what you're doing and the result you're getting, you'll see, you'll analyze it, you'll see that it really makes perfect sense. Okay? So now